Okay, guys. Shh. So we're going to attempt to do an integral here that looks like this. Now, this section is called logistic growth, but really that's only half of it. The first half is doing integrals involving partial fractions, so we're going to start with that and then get into the logistic stuff later. So if we had 2x plus 16 over x squared plus x minus 6, up to this point, the only methods we have for doing integration that isn't just straight ahead like ones you have memorized from derivatives, which this is obviously not one of those, would be to maybe try a u substitution or do integration by parts. Now this one is not a multiplication of two things, so integration by parts is not exactly going to work, right? And if we try to use substitution, seems like that one maybe would work if you chose like the denominator to be the u, okay? But then if you did the du of that, it would be 2x plus 1. And we need that to cancel the numerator. And does that cancel the numerator exactly? This is 2x plus 16. So it would not cancel that out, right? So a u substitution breaks down in this one too. So there's no way to do this integral directly. So what we have to do is, if you need to break it into a couple of parts, and we call them partial fractions. Okay, we did a little bit of that in pre-calc. So we're going to take the integral sign off of this thing for just a second. Well, more than just a second, but and we're going to think about how we could rewrite this thing. All right, and so we're going to break it into two fractions, and each one is a part of the original. So the denominator of that original fraction can be factored, and those two factors are going to be the denominators of our two partial fractions then. Okay, so what two factors make up x squared plus x minus 6? Got to multiply to negative 6 and add to 1. All right, negative 2 and 3. And there's going to be some kind of numerator for this one and some kind of numerator for that one. And for now, we'll just call them a and b. And we've got to figure out what those are. Now, here's the thing. If I can figure out what these two numbers are, a and b, think about this integral. The integral of this would be equal to the integral of this plus the integral of that. If this was just some number, say it's a 2, can you do the integral of 2 over x minus 2? Absolutely. Can you do, let's say this was a 3. Can you do the integral of 3 over x plus 3? Yeah, absolutely. Okay, so this is accessible if we can figure out what these two numbers are and break it into that and do the integral of this stuff instead of that. Because we know it's equal, so it should still be the same answer. All right. So, anybody remember the process that we took from this stage to find the a and the b? No? Okay. Well, if you take, actually, not there, the whole thing. If we multiply this entire equation by x minus 2 and x plus 3. Think about distributing that thing to each part, okay? Remember, x minus 2 times x plus 3 is equal to x squared plus x minus 6. So if I distribute both of those and multiply it with this first fraction, what do I get? (2x plus 16). Okay, if I multiply this by a over x minus 2, what do I have? Times the a still, right? What about the next one? B times x minus 2. Okay, and so here's where we came up with a little system of equations where the coefficients on x needed to match on either side, and then the constants needed to match. So If I do a little distributing here and rearranging, this and this needs to be the same, and this and that need to be the same. So 2 needs to equal a plus b. Right? If I have 2x, the a and the b together need to give me that 2. And then also the 16 needs to equal 3a minus 2b. So I got a little mini system of equations here where I can do substitution, elimination, that sort of thing. So I'm going to take this equation times 2. So we got 4 equals 2a plus 2b. And then still get that 16 equals 3a minus 2b. If I add those two together, I got 20 equals a, because the b's are gone now, right? So a is 4. Everybody follow me there? I just did some elimination. And then if a is 4, what's b going to need to be? If you go back to one of those original equations with a and b there, if I were to plug a 4 in for a on either one of those two, what do we get for b? All right, so I've got a and b. So now my partial fraction decomposition is what it's called. I can rewrite this integral then as being the integral of a over x minus 2, which was 4 over x minus 2. And then b was negative 2, so minus over x plus 3. So this original integral I can do like that instead. So what is the antiderivative then of 4 over x minus 2? What's the integral of 1 over x? So what do you think it is for 4 over x minus 2? You got it. Four natural log x minus 2, and then minus and then don't forget the plus c, right? Yeah, there it is. All right, so it takes a little bit of work. These are a little lengthy, okay? You got to go through all this fraction business over here. Coefficients a and b, and then use that to rewrite your partial fractions, and then you can do some natural log work with the antiderivative to get the answer then. Okay? Gives you a means to get there. So let's try. And then we'll see where we're at with time, with how much more I can do here. So how about say f of x is equal to x minus 13 over 2x squared minus 7x plus 3. All right, and I want to find the integral of f of x dx. Okay, so you guys tell me the steps. Like, you tell me what to do next, and I'll do it. Okay? So what should be the first thing I do here? Factor the denominator. Okay. So I'm going to save you some time here a little bit. If we factor the denominator, just because I know you guys know how to factor, and I don't want us to spend a ton of extra time trying to do that. But that denominator factored is 2x minus 1 and x minus 3. Okay. Now what? Done. Next. Okay. So if I do that multiplication, now I've got x minus 13 equals times x minus 3 plus b times 2x minus 1. Okay. Now what? Okay, distribute the a and the b. I'll do a little rearranging here after I do that as well. Okay, put my x's together and the constants together there, kind of like we did the last one. Okay, now what? Good. So 1, because it's 1x, equals a plus 2b, and then the negative 13 equals negative 3a minus b. Matching up my constants there from one to the other. What now? Okay, do some elimination. How would you like to do that? What do you think I should multiply by? And which equation? Bottom 1 by 2. Top also been pretty good. So 1 equals a plus 2b. Now we've got negative 26 equals negative 6a minus 2b. Add those up, so that's going to be negative 25 equals negative 5a, and that's gone. So what's a? Take a look at one of your original equations there. If a is 5, can you get b? Can you do that in your head real quick? I would maybe try the top equation there. That's the easier one. That would be, yeah, negative 2. So our integral then is going to be what? So if I did a minus sign here, that would just be positive 2 though, right? So we can just do it like this. So this one, I'll kind of take it the rest of the way here now. So it's going to be some natural log work. However, there's some chain rule business we got to take care of here too a little bit. This would be natural log of 2x minus 1. Derivative of that thing, you'd have a chain rule to take care of. You'd have to multiply it by 2, right? So what do I need to do? Divide that by 2, right? And then minus 2 natural log x minus 3 plus c. Now that one, I don't have to worry about that. Do you guys see that? Because it's just x minus 3. There's no coefficient on x. So the derivative of that would have been 1. Multiplying by 1 does nothing. So it doesn't affect. Now, how you're going to see this written, just for clarity's sake, be something like this. Okay. Now, your particular textbook likes to kind of take the answer even further using some properties of logs. Okay. So I'm going to show you what your textbook would do with an answer. For me, it doesn't bother me so much if you do this or not. But just so when you're checking your answers, just so you know, here's what they'll do. Bless you. Everybody see what they did there? Okay. So if you're like looking at your answer, you got all your natural logs in a nice little row, and then you look it up in the back and you're like, what the heck? That's what they're doing. Okay. They're combining the logs into one log to write the answer. Okay. Both are equivalent, both are acceptable, but your textbook takes it all the way. The AP exam does this as well. Okay, so it might not be a bad idea to get in the habit of writing your answers that way. Okay, but for me personally, I will take them either way. Now, if it's a multiple choice question on a test, maybe I do this. So it wouldn't be a bad idea to at least give it a shot with each one of these and just kind of see if you can get it to match what they've got. Okay, so okay. So let's talk about the logistic differential equation while we got some time, and then we'll be done. Okay, we talked about this a little bit in pre-calc, some at the beginning of this class as well. Exponential equations by themselves don't really model population effectively, right? It's because of the fact that there's a limited amount of space that we have to exist, or an animal maybe is caught in a nature preserve, there's only so much space they have. Populations are going to level off eventually. They don't just keep going up. So logistic equations are a better means of modeling population than an exponential equation is. Okay, so your exponential one we already looked at. I'm going to just rewrite that over here. The exponential differential equation was, I guess we're doing p and t for population and time, dp dt equals kp. All right, that one should look familiar by now. The logistic differential equation, dp dt, this one is kp times m minus p. Okay, and m is the carrying capacity. You guys remember that from logistic equations, the carrying capacity? That's that how big can it get number. It's at that horizontal asymptote when you graph it that it approaches as you go. Okay, so the differential equation for that looks like this. dp dt equals kp times m minus p then, okay? So you need to know a little something about carrying capacity, construction things. They will give you the differential equation, and then if you can recognize, oh, that number right there, that's the carrying capacity, use that to help answer some questions about it, okay? So we're going to talk about moose here using this logistic equation. So this is actually, I'm stealing this out of your textbook just so you know, but the Michigan Department of Resources airlifted 61 moose from Algonquin Park to Marquette County in the Upper Peninsula. It was originally hoped that the P would reach a carrying capacity of about with a growth rate of this. So this is the moose in their new home. They're hoping that this is going to be the growth rate for them. Okay, 0.0003 p times 1,000 minus p. Okay, see how that is a logistic differential equation, fits that form? Okay, what's the carrying capacity of this moose preserve? 1,000. They're hoping it can get up to 1,000 moose in that place. Okay, for that situation as well. Is what is the carrying capacity, and you already told me. And the plural for moose is moose, right? Yeah, okay. So it's 1,000 moose. That's a slope field thing. We can, yeah. With initial condition P0 equals 61. In the question that I read to you, it said that they airlifted 61 moose to this preserve. So our initial population of moose is 61. So P of 0 equals 61. All right, so we got to solve the diff EQ. So first things first, we need to separate the variables. Okay? So if we separate these variables, here's what we're going to end up with. Okay. Do you see how this is going to end up being a partial fraction problem? Take a look at the left-hand side. The right-hand side of that, no issues, right? It's just dt, easy. The left-hand side, doing this with p, I've got essentially 1 over 0.0003p times 1,000 minus p. So I have a little thing I need to take care of over there then. So if I do this integral step here, over here, I'm going to have 1 over 0.0003p times 1,000 minus p. So I need to break this into a over 0.0003p plus b over 1,000 minus p. Kind of what we were just doing, right? Now, here's one nice thing. And I just wrote this way just so you guys could see how it comes into this just like before. It's really ugly. It makes this really hard to do. Okay? Do you see how over here in this big fraction, I could just take that and just pull it outside the integral, right? 1 over 0.0003, I could just slide that outside because it's really just getting multiplied by the whole thing, right? So I don't need to keep it in there necessarily, which makes my calculations right here a lot nicer. Okay? So that's what I'm going to do. Okay? So sorry if you're writing in pen, but I'm going to turn this into a p. And so this was just p, which means this up here, if I'm doing 1 divided by that, that's going to be the number up front. So 1 divided by 0.0003 is 3,333 and a third. So that's just going to be outside the integral. So once I'm done doing all this work, I'll by that at the end, okay? So here and get this thing taken care of. So if I multiply by p times 1,000 minus p, I'm going to end with 1 equals a times 1,000 minus p plus bp. And so if I match up my variables on either side, I got no p over here, right? So that's going to be 0. And then what's multiplied by p? Well, I got minus a plus b with the p's over here if I distribute this a into there. This 1 is equal to all the constants over here, so it's 1,000a, no b, right? It's just b times p, that's it. So this one is actually pretty easy to solve once we got that all put together, because look, here's a, right? 1 equals 1,000 times a, so what is the a? It's 1 over 1,000, right? Okay, it's a little bit of an ugly number, but it works. Is 1 over 1,000? What's b? It has to equal 0. Negative 1 over 1,000 plus what? 1 over 1,000 again, right? Okay, so my two parts I'm going to use for this thing. So let's see. So I'm going to do the integral. So this is all one thing. And then don't forget I got 3,333 and a third still hanging out front here. Same thing here and here, so I could take that and pull it out front too, right? So if I 3,333 and a third by 1,000, 3 and a third. So that's what I'm going to do right here. I'm just going to take these guys and factor them out. So it's 3 and a third. 1 over p plus 1 over 1,000 minus p dp. And now I can do this pretty easily with my natural logs again. So it's 3 and a third natural log of p. Okay, so I got minus p in here, right? So it's minus the natural log of 1,000 minus p. Plus c. So that is, if we go all the way back to up here, this whole business here is this side. It still equals the integral of dt, right? So I got to take this, and then it's technically equal to the integral of dt, which is just t. And then the initial population, they said p of 0 equals 61, which essentially means that t equals 0 and p equals 61. Okay. So, running out of time here, but here's what I'd like you to do. Take this thing, plug in a 0 for t, plug in a 61 for p, solve it for c. Okay, you can do that, right? Figure out that constant c then by plugging those two numbers in. And you're done with that. Turn to page 367. And on the top of 367, they're finishing this problem for you. Okay? And I want you to follow along with that and write that into your notes, what they're doing there on that page, to finish it up. Okay? And that's going to give you your final answer for this thing. Okay? So, your assignment, course sites. So you can check it out there. In your reading, which will be helpful, 57, they've got this. If this is the differential equation, here's the solution. It's another little shortcut. Okay? So if you don't want to do all the separation of variables and that sort of thing necessarily, these match up as well. So that's a little bit of a shortcut for you to take a look at as well there. But, okay. So I'm stop, and then we'll meet back on Wednesday then.